Hello. Well, I guess we know the two of us are here, and we see a little counter that says that other people are here too. So, welcome to our event, our Wednesday event. Feels like a series now. And I am Ann Merchant, and I am joined by.
I'm Rick Lover.
Thank you very much for being here. We hope all of you are well. It's funny, I think I had said last time that as we live in the world of Zoom and live through our computers, there's been sort of fun things that we've been seeing online, some of which we wanted to share. I saw an auditory love letter from the New York Public Library. And so they have recordings of familiar city sounds. So taking a taxi to anywhere. One of them was called Romancing Rush Hour. And it was Serenity in a Rowdy Park. And so all the sounds of a city that we took for granted, it's kind of nice to hit the little play button and hear some of that again, because it's not what I hear out my window, and I'm not jumping in any taxis. I thought that was kind of interesting. I also received my own food substitution Bible, because there are a lot of things I don't have. I look at recipes and I don't have them. So it's kind of nice when I have now a food substitution Bible. And I also watched a virtual sheep competition coming out of the Lake District in England with 4-year-olds leading their sheep around. I highly recommend it as a distraction if you have a few moments. But what we're very happy is that when you need a distraction, you've turned to science and you've given us a few moments. So we're really happy about that. And in the process, I think what we wanted to do is to explain a little bit about the National Academy of Sciences. And then Rick will talk about the Science and Entertainment Exchange to give you some context. So the National Academy of Sciences is a private nonprofit institution in Washington, D.C. We were created by Abraham Lincoln in 1863. I think I just said that. And so we've been doing the same thing for more than 150 years, which is to provide good, solid, evidence-based advice to help make better policy, and policy that intersects with science, engineering, and medicine. As you might imagine, we're pretty busy these days because there's a lot of science policy that needs good advice from experts. And so that's a lot of what the institution is focused on. Today, I believe, is National Nurses Day. I think we all feel like that's the moment where we want to shout out to nurses, because they have become an especially important part of how we're dealing with current events. But the academies has done a lot for nurses over time. We have decades worth of reports pointing out the importance of nursing, and those nurses who get PhDs, for example, how they make contribution to the nursing landscape. So it's a good day to celebrate them and to give them a shout out as we start our event, and the way that the academies has certainly recognized the profession over the years. But the academies about 11 or 12 years ago created the Science and Entertainment Exchange as a way to communicate science more broadly through the medium of film and television. And Rick is the director of the Science and Entertainment Exchange. He's in sunny Los Angeles. I'm in rainy Maryland. He's got better weather, and so I'll hand it over to you to talk a little bit about the exchange.
I don't know, it's like 93 degrees outside. But anyway, I want to thank, well, I should say I'm Rick Lovard. I'm the program director of the Science and Entertainment Exchange. First, I want to thank our AV team at the NAS, MHA in particular. You have saved our bacon multiple times through these events, so thank you. I want to thank everybody in the DC office, and Courtney Sloan, Jeff Fishman, and of course, Sachi Gerben, who works with me here in LA. Lastly, I want to thank actor and host of the Afrofuturist podcast, Ahmed Best, for live tweeting today's event. Please check out his podcast. It's awesome. So for those of you who don't know, and by our polling, about 40% of you have never been to one of our events before, the Science and Entertainment Exchange is a program of the National Academy of Sciences. If you are a writer, director, producer, studio executive, you're creating a video game, a TV show, and you have a question about science or a movie, you have a question about science, you call us and we will connect you to a field expert for free who has volunteered to give you some advice on your project. We've done over 3,000 consults since we opened our doors, including Avengers Infinity War, Man of Steel, Black Panther, and Captain Marvel. As you can see, we only work on indie films. And we've done over 300 live events, including now all these virtual events from quarantine, live from quarantine. If you are a STEM professional and you're new to our audience, please send us an email. Let us know that you're interested in connecting, because we are happy to connect you to folks who are making creative media out in the world. And I would be remiss if I did not thank our sponsors, Howard Hughes Medical Institute, who makes these events happen. Thank you. Alfred P. Sloan Foundation, Walt Disney Company, Film Nation, Google, Lida Hill Foundation, Corteva, and individual donors like many of you. Look, I know we live in a wild time right now, and facts and science matter more than ever. And here at the NAS and at the Exchange, we're doing whatever we can to be a resource and hopefully a point of inspiration for you and your work through events like these. I know a lot of people do not have the ability to give right now, and I completely understand that. But look, if you like our programming and you do have the means, please do consider a donation. I want you to know that those donations are absolutely critical to making these events happen. So a little bit about the event structure. We have one speaker today who Anne will let us know a little bit more about in a moment, but at any point, there's a little down here, there's like a little thing that says Q&A with a little like comic book bubble coming out of it. If you click that at any point in the talk, I'm gonna be scanning it and I'm going to be organizing the questions to give to Kirk at the end. We have a limited time for Q&A. My apologies if we do not get to your question. I do my best at getting to as many as I can. So thank you very much, and without further ado.
Yes, I will take it back only to pass the baton because what you're really here for is to hear from Kirk. You know, maybe I was a little bit opportunistic, but I began to think about as we were doing our virtual events, wow, I bet there are some people that are probably not traveling right now, perhaps not having such a busy calendar with their speaking engagements. Who might some of those people be? And at the top of my list was Kirk Johnson. He is somebody whom we have wanted on our exchange stage for a long time, but as the director of the National Museum of Natural History, as you might imagine, he's usually a very busy fellow. Not to say that he's not a busy fellow now, because he's still running a museum, and that's still very much a full-time job. But he isn't on airplanes and he isn't on stages all over. And so we were very fortunate to have him say, yes, I think I can do this. I don't really, you know, we don't do a lot of introductions with big CVs, but Kirk, I will just tell you that I have seen him talk about his work. He actually one time showed me a fossil that he had by hook and by crook, I think, managed to collect. And I still have a picture, which he told me never to share, so I'm not going to show anybody, but it was this amazing fossil that was just like perfect. And it was sort of the first, at that moment where like the person that directs the Museum of the Natural History is telling you about this fossil. It was sort of a moment that sticks in my mind. And I'm sure that whatever Kirk is going to talk about today is going to stick in our collective minds, because he's an amazing speaker with an amazing job. And we're going to hand it over to you.
Thanks, Anne. It's really fun to be here and sitting actually in my office alone in the Museum of Natural History, but it's a good place to be. And I'm going to start right in and talk today about deep time polar climate, like what was the past like in the Arctic regions. And I'll tell you how I got into this whole thing, because it started a long time ago for me. But first, think about this. Trees are all over the planet, but they're not evenly distributed around the planet. In fact, trees are in bands. They're in the bands of the boreal forests and the tropical forests and the deciduous hardwood forests. There's about 3 trillion trees on the planet right now. There were probably 6 trillion trees when people started chopping them down. And there's about 60,000 species of trees. So they're really pretty interesting. What makes them so interesting to me is that trees have been around for a long time, and individual kinds of trees have been around for a long time. So some different genera of trees, for instance, have been alive for more than 50 million years. That means that trees tell you about the history of the planet because they're not living today where they used to live. Now, balancing trees on the other side of this story is polar ice. If you want to find polar ice, you go to the poles, the North Pole or the South Pole, and both poles have polar ice caps, both floating sea ice shelves, and actual thick caps of ice on the land masses like Greenland and Antarctica. So in a way, this story is really about forests and ice and the dance between forests and ice on planet Earth. Now, to do a story like that, you need a paleobotanist, and I happen to be a paleobotanist. That's me with one of my high-tech tools. Paleobotany is a science that still relies on high-tech equipment like pickaxes and shovels and hammers and knives to get the fossils out of the ground. And fossil plants are really remarkable things. Here's a fossil leaf from British Columbia, and you can see that this thing fell off a tree 50 million years ago, landed in the bottom of a lake, and 50 million years later, we have this incredibly preserved specimen can see the veins. The veins of leaves are like the fingerprints on criminals. You can identify fossil plants by the patterns of veins in the leaves. But leaves also tell you about how much rain was falling when the tree was growing, how warm it was. And insect bites on the leaves actually tell you which insects were around and that were predating the leaves. So fossil leaves are more or less like fossilized little weather stations. And since a single tree might have 1 million leaves, they're pretty common as fossils as well. So if you think about that, how could you not want to be a paleobotanist? And as I drive around as a paleobotanist, I look at ancient landscapes, and you might see a coal mine in Wyoming, but I actually see the swamp that made that coal mine. So when I look on landscapes today, I look at outcrops of rock, and I see the ancient worlds that were caused by eons and eons of deposition, burial, and uplift. So as a paleobotanist, I started as a young kid. In fact, when I was about 12, I started going to the Burke Museum in Seattle, where I met an artist who was an amateur paleobotanist. He loved the beauty of fossil leaves. And when I turned 16, I got a driver's license, and he and I drove off to this place called Republic, Washington, because we'd heard there might be fossil flowers at this site. And we, here's the town of Republic, Washington. That's not me in the picture, by the way. That's just a little kid in the picture. But right where that kid is, right at the edge of the road, at the edge of town, I kicked a rock, and the rock is kind of an interesting rock. It's this flat, layered rock called paper shale. When you split paper shale, it's like opening the pages of a book. And it's ancient lake bed deposits. And when I was 16 years old, I kicked a rock, and up popped this very rock. And you can see that on both sides of the rock are the mirror the image of the same fossil plant. It's a plant called metasequoia, or the Dawn redwood. And I was amazed at how beautiful that thing was. My artist friend was amazed at its beauty as well. And I didn't know at the time, but fossils are real messengers from the past. They tell you stories about our history of our planet. And in fact, we dug in that little ditch by the side of the road, and we did find fossil flowers there. And there's the idea that it might be fossil flowers there was actually true, and we found this incredible fossil flower. And we kept digging, and the site produced a myriad of plant parts from over 200 different kinds of plants. Remarkable things: the pods, the seeds, the flowers, the cones, the needles. It's a whole world preserved in this paper shale in eastern Washington. One of the fossils we found was this thing called metasequoia. It lives today. It's a deciduous conifer that grows in central China. It didn't occur to me then, but it started to occur to me, like, that's odd that a tree that lives today in China is in the side of the road in eastern Washington 50 million years ago. We found this thing, Cercidophyllum, the Japanese scholar tree. Again, a thing that today lives only in Japan and China, 50 million years ago was living. These plants were growing in a forest that today we would call a broadleaf deciduous forest. And today, those kinds of forests occur naturally in 3 places: Eastern United States, Western Europe, and Eastern Asia. And in between those areas are huge expanses of non-deciduous forests, things like boreal forest or Arctic tundra or dry plains and grasslands. So it's a big question: how did these similar kinds of forests end up so separated from each other? And what in the world are those fossils doing in Republic, Washington? Well, I finally got around to answering that question when I met this woman. This is Mary Dawson, who's a curator at the Carnegie Museum of Natural History in Pittsburgh. And Mary Dawson had been working in the high Arctic since about 1976. I heard about her in 1982, and she had been working on this island at the very top of Arctic Canada called Ellesmere Island. And it's a big island. It's about the size of England, and it's essentially uninhabited. There's one village of Inupiat people at the very south end of the island, but it's a huge, largely uninhabited island. And Mary had been going there to study fossils of animals that would live there 50 million years ago, with the idea that she would understand the history of fossil animals in North America. And I met Mary, and I met Leo Hickey at Yale University, who was a paleobotanist. And I said, I have to go with you guys to this place. I must go. And miraculously, they let this 23-year-old Kirk Johnson join them. And here I am with Mary at Resolute Bay in Ellesmere Island in 1984, heading out. We hopped, the 4 of us hopped in this little tiny plane, flew 600 miles north to Ellesmere Island, landed on the tundra, unpacked our gear, and there we were looking for fossils in the high Arctic of Canada. And today on Ellesmere Island, there is nothing for vegetation. The only woody plants are little prostrate thing called the Arctic willow. This is about as big as it gets. But as you drive around, there are huge ice sheets on Ellesmere. This is an ice cap that's about 1,000 feet thick where we can see it. You can see a waterfall at the edge of it. Here I am standing at the base of this waterfall. This is the Ice Age. It's a real polar area. But as we flew around in helicopters, we found coal seams. And the coal seams have these white, crumbly rocks in them. If you go close to those crumbly rocks, they turned out to be actual fossilized tree trunks. And you would find whole forests of these tree trunks. We rummaged around in the bottom of the trunks and found actual logs. You can see the growth rings in the logs. And here we are more than 1,000 miles north of the nearest living tree in fossil forests. That was kind of a mind blown for me back when I was 23, and it's still a mind blow for me now. And here we found these gigantic trunks. These weren't just small trees, these were huge trees. And what were the leaves? The same leaves I was finding in Republic, Washington, the leaves of metasequoia, the leaves of cercidophyllum, a Japanese scholar tree, leaves of ginkgo. The same things I found by that roadside in Washington state were growing in the high Arctic 50 million years ago. We found a really odd thing that had this radiating pattern. And unless you're a botanist, you might not recognize this one. This is actually a fossilized lotus leaf. Fossil lotuses in the high Arctic. Here's what the high Arctic looked like 50 million years ago. It's a far cry from what it looks like today. Mary is a vertebrate paleontologist. And what she does is she crawls on her hands and knees and looks for tiny remains of ancient animals. And animals that she found in the high Arctic were incredibly surprising. She found things like this little skull. You can see the row of teeth. You're looking into the palate of a small mammal. This is the skull of a flying lemur, a kind of animal that lives today in the rainforests of Indonesia. But here's a flying lemur flying amongst the Japanese scholar trees of the high Arctic. She found fossil turtles. Here's a turtle shell. She found crocodile and alligator fossils. So you're starting to put together an ecosystem that's not a lot like an Arctic ecosystem. And she found the bones of an extinct animal called a Crifodon, a sort of a hippo-like animal that wallowed in swamps. So this is a painting done by Cliff Morrow that shows turtles, alligators, lotuses, Griffodons, and forests where today there's Arctic tundra and ice sheets. That says something about climate change. Here's a diorama we built for this reconstruction at the American Museum of Natural History, the same extinct Arctic ecosystem. Then in 2004, scientists drilled a well in the bottom of the Arctic Ocean on the Lomonosov Ridge, out in the middle of the Arctic Ocean, which is an ocean that's covered by floating sea ice. And they found in the core, in sediments that were 47 million years old, the remains not of icy water organisms, but in fact, a floating aquatic fern called a zola, which grows today on lakes in tropical and subtropical regions. They found that at the bottom of the Arctic Ocean. So here's the Arctic Ocean today, and here's the Arctic Ocean 50 million years ago. A sea of floating ferns, a totally different Arctic than we have today. And it really does stop and make you think, why was the Arctic so warm then, and why is it so cold today? So we have these two terms, and as we think about the history of the planet, we talk about icehouse world, the time of world we're in today, where we have ice caps and poles, and hothouse worlds, where there are in fact no polar ice caps. And today's talk is about the differences between icehouse worlds and hothouse worlds. In an icehouse world, there's sort of two flavors. There's the times when there are cool periods, like the ones we're in right now, and there are times when there are cold periods. In the cold periods, the ice comes down and meets us. So today, in a cool icehouse Earth, we have ice on Greenland, but that's where it is. In a cold icehouse world, what we'd call an ice age, the ice comes down to mid-latitudes and covers us up. Now, I grew up in Seattle, Washington, 18,000 years ago, was covered by 3,000 feet of polar ice. So Seattle wouldn't even have been there. And if you go to Seattle today, the Space Needle is 605 feet tall. And my friend Ray Troll did a nice little graphic that shows just exactly how much ice was on top of Seattle. There were 5 Space Needles full of ice on top of Seattle a mere 18,000 years ago during a cold phase of icehouse world. And the icehouse animals, the animals that we see remains of today in the Arctic, and some that went extinct, things like mammoths and mastodons, but also things like musk oxen. People drilled cores in the ice sheets in Antarctica and Greenland starting in 1969 and got incredible patterns showing the history of Earth's climate over the last, in this case, 800,000 years. And you can see that we go from cold to cool to cold to cool to cold to cool. And if the top line on this graph shows carbon dioxide, which goes from about 180 parts per million to about 280 parts per million until it gets right over to the far right-hand side where it shoots way off the curve. And of course, what you're looking at there is what we call the Keeling curve. That is the observed increase in carbon dioxide in the atmosphere that's happened, in fact, in my lifetime. On this curve, you see 1960, the year I was born, at the bottom lower left-hand corner. And on the right, you see today, April of 2020. And the amount of carbon dioxide in the atmosphere has gone up from 315 parts per million all the way up to 415 parts per million. 25% increase in the time that I've been on planet Earth. That's enough to make you think that something is going on planet Earth. And we know that humans are emitting carbon dioxide at an unusual rate. They're just not absorbing it, and it's building up in the atmosphere and warming the Earth, which makes us think about, well, could we go back to a world with no ice? Let's talk about the hothouse world. In the hothouse world, you have two conditions. There's no polar ice in any case during the hothouse world, but you have times when it's warm and there are polar forests that are temperate, and times that are hot where subtropical forests make their way all the way up to the tropical regions. And I'll use palms here as an example. Palms you might have thought about a little bit when you're thinking about your vacation, because palms live in warm places. There's about 2,000 species of palm trees today in the world. Some are not trees, but most are trees or vines. And they live in places that are pretty much warm. The equatorial regions, dry deserts, tropical rainforests. In fact, palms don't grow where the ground freezes. So let's take a look at fossil palms. Here's a fossil palm frond from Wyoming, not known for being a place that's warm and sunny all year round. In fact, the ground freezes pretty hard in Wyoming. So the fact that you find palms in Wyoming make you realize that Wyoming used to be warmer than it is today. Here's a fossil palm on the road cut near Bellingham, Washington. And when we were filming the Nova show called Making of North America, we were filming on an island off of Sitka, Alaska, filming for something else. And much to my amazement, we popped up a fossilized palm frond on the beach in Alaska. And that made me think, how far north is the northernmost fossil palm? Here's the palm we found in Alaska on the beach near Sitka. And then we headed north of Anchorage, Alaska, to a place called the Matanuska Valley, where someone had suggested they might have seen a palm frond. And here we are using a tool known as the Alaskan climbing stick to climb up a vertical surface. And that little hole right above the guy in the blue shirt actually has a fossilized palm leaf sticking out of the side of the road north of Anchorage, Alaska, that's 60 million years old. So here's your mind bender. Here's all these fossil sites, and you realize that the west coast of North America was a tropical to subtropical to warm temperate forest all the way up to Alaska. Here's a reconstruction of what Anchorage would have looked like 60 million years ago, a palm and broadleaf forest. Kind of a weird, different world. Now, we can jump to the other end of the world and we find the same sorts of things. This is Marcelo Lepe, who's the head of the Chilean Antarctic Survey. Here we are filming the Polar Extreme show for Nova that just aired in February. And we're on a beach in Antarctica, and the fossils on the beach are broadleaf forest trees, the same kind of deciduous forests that today are located only in a few places, but in a much warmer world, these forests covered both poles and there were no polar ice caps. We saw this at the cover of Nature magazine just April 2nd of this month. Title of this article is Evidence for a Temperate Rainforest Near the South Pole 90 million years ago. So it's well-studied science. The polar regions have had long periods when they weren't icy, they were just polar. They still had the polar dark periods, but they were forested ecosystems that had a lot of animals and plants that live today at mid-latitudes. So when we were building the Deep Time exhibit, which opened on June of last year at the National Museum of Natural History in Washington, D.C., we knew that we wanted to embed a long strand of what Earth's climate history has been over the last 500 million years. We pulled together a team of paleoclimatologists, people that study ancient climates, and charged them with making us a climate curve for the last 500 million years. And here's that curve. You can see that there's 500 million years of time on that, and the bright red line that runs right across the middle of the curve is the line that marks warm times and cold times. When the curve is above the line, there are no polar, there are polar forests, but no polar ice caps. Below the line, there are ice caps. You can see that more or less about 75% of the last 500 million years of planet Earth, there have been no polar ice caps on the poles. So the condition we have today is the uncommon condition. You can see over on the far right-hand side of the curve that we're still in a time that has polar ice caps, But you see, it's possible for the climate to change enough to lose the ice on planet Earth. And that, of course, is what we're concerned about as we go into a global warming phase. And here is a curve that shows the last 20,000 years as we came out of the last ice age. And you can see for the last 10,000 years, the climate didn't change very much. In fact, it was pretty constant and smooth. And it's during that time that human civilization evolved, agriculture was formed, cities were built, and we as humans lived in a world that had very low fluctuations of sea level, pretty constant climates, not so many droughts, perfect for agriculture and civilizations. But once that Keeling curve kicks in, once humanity starts emitting the carbon dioxide we're emitting right now, we're putting out like 50 billion metric tons of carbon dioxide a year in emissions, we have started to push the climate curve straight up with the carbon dioxide curve. And on this graph, you can actually see that little tip upwards, and you can see today where the mean annual temperature of the planet's around 60 degrees Fahrenheit. If we get 4 or 5 or 6 degrees Fahrenheit more warm, we'll go into the place where polar ice caps are no longer stable on planet Earth, and we'll be moving back from an icehouse world to a hothouse world. And that's the challenge that faces us. And you probably can't see those two little bubbles next to the curve. One of them shows how much of the National Museum of Natural History will be submerged by water under certain levels of ice melting, and how much will be covered under complete levels of ice melting. If we were to melt all the ice on Antarctica and Greenland today, we'd raise sea levels by about 215 feet. So it's a significant change. It will happen over a period of hundreds of years, but that process has begun now with the warming of the planet. So this story I've just told you is presented in NOVA's show Polar Extremes, which you can easily get to by just Googling NOVA Polar Extremes. And you can also take a tour of the National Museum of Natural History's Deep Time Hall by just typing in National Museum of Natural History Virtual Tours. With that, I'll stop and take questions.
Hey, sorry about that. So first question we have is sort of general riffs, I'd say, on geoengineering. Do you have any thoughts about various attempts to manipulate the environment on the other side?
Well, I think, this is the challenge we have now is that now that we're warming the climate by adding carbon dioxide, are there other ways to cool the climate? And we know that you can cool the climate by putting aerosols in the atmosphere, but they tend to drain out of the atmosphere pretty rapidly. And the big difference between aerosols and CO2 is CO2 will stay up for thousands of years, where aerosols will stay up for dozens of years. So geoengineering tricks to cause local or temporal cooling would have to be continuously applied over long periods of time. It would be hard to know exactly how those impacts would be felt in different regions. So that's one of the challenges of geoengineering from my perspective.
Do you have any thoughts or observations about fossils that are along the equator, not just the poles?
Yeah, we've been looking very much at this very interesting geological question of when and where did the first tropical rainforests appear? And there's a fair amount of evidence that in the warm times when there were polar forests, that the equatorial regions were actually quite warm and dry, and maybe too dry for tropical rainforests. And that in fact, the first rainforests of the world may have been in mid-latitudinal bands where it was warm enough and wet enough for tropical rainforests to flourish. And the tropical areas themselves, two things. One, they were probably too warm and too dry for forests, but a lot of them at that point in time, back in the Cretaceous period, actually the continents had not come together, and there was not that much land at the equator, say 100 million years ago when tropical rainforests were first flourishing. So it's a different world indeed. And this story of tropical forests and polar forests is sort of a dance of the climate through time.
So are there other ways that the continental drift factors in when you're looking for fossils?
Well, definitely. I mean, the study of continental drift, which really became quite popular after the 60s, allowed us to know that not only do we know that the continents are drifting, but because we have the magnetic signals of the continents preserved in their rocks, we know where the continents were when they were there. So we can actually make these very detailed paleogeographic maps. And basically, the simple way to think about it is that when continents move, they leave what I call skid marks. They leave a trail in the ocean where they've been in the magnetic signals. So we can make these maps and reconstruct ancient geographies and map onto those ancient geographies ancient climates. And so, one of the people would say, well, maybe those fossil palm fronds that you found in Alaska were palms growing at lower latitudes that then drifted north. And there are examples of that happening, but much of the knowledge we have is that there really were forests in the high Arctic and Antarctic regions.
So as you look at current land masses and you consider sea level rise if we lost the ice caps, can you speak a little bit to how much land would still be around and how humans might adapt?
Well, I mean, it's pretty easy to do. You just look at a topographic map and say, where is the coastline gonna be if the sea level goes up 100 feet or 200 feet? So, if you melt all the ice, you're gonna get a little bit more than 215 feet. So that's your maximum. So there's plenty of continents that would not be submerged, but so much of humanity and so much human infrastructure lives right along the coastlines that a total loss of both Antarctica and Greenland would be devastating to human civilization on the coastlines. What we're thinking by the end of the century is at least 3 feet of sea level rise, and maybe twice or 3 times that much, and maybe 3 feet, 6 feet, or 9 feet of sea level rise. So this loss of the ice sheets isn't going to happen in this century, but it'll be baked in to future centuries. And certainly even 3 feet of sea level rise will have a huge impact on coastal infrastructure and humans living along the coastline.
So you won't be passing down your beach house to your grandchildren?
No, I think that's something to be enjoyed in the immediate future.
So what caused all this climate change before humans were around to mess with the climate?
Yeah, it's basically the climate is being driven by the position of the continents and by the composition of the atmosphere and the resulting currents in the atmosphere and the oceans. And the prevailing logic is that it was increased greenhouse gases in the atmosphere that caused warmer time periods. And the way you do that without humans is the emission of carbon dioxide from volcanoes. So long periods of time, carbon dioxide builds up, and it slowly builds up in a warmer condition. And the way you get rid of the carbon dioxide and cool the planets before there are humans is by the weathering of rocks through the uplift of mountains. That draws the carbon dioxide out of the atmosphere and turns it into rocks and sediments. So there's a rock cycle that both naturally creates carbon dioxide and consumes carbon dioxide. And the warmings and coolings in the past are perfectly natural, but happening at a much slower rate than what we're doing now. Because what we're doing now is we're mining coal and oil and natural gas, and we're excavating calcium carbonate and limestone to make concrete. All of those things are taking all those fossil carbon atoms that were buried over hundreds of millions of years, and we're exhuming them and putting them back in the atmosphere in a period of decades.
So is there anything that's happening right now in this few-month window when so many people are under quarantine that is impacting climate change projections?
Well, what we're seeing is a couple of things. The decrease in air travel, and the fewer people driving, we're seeing cleaner skies. We're seeing not as much aerosol pollutant. And so there's stories of people in India who've never seen the Himalayas before. Suddenly the clouds have cleared up and the smog is blown away. They're seeing the Himalaya mountains for the first time. And many of us have experienced that. If you live in Seattle, you get the mountains are really brilliant right now because there's nothing blocking the view. But that's the short-term pollution of lofted particulate pollution. What we're also seeing is a decrease in the use of fossil fuels because people aren't traveling as much. So there's going to be a slight decrease in the amount of carbon dioxide we emit into the atmosphere, but it's nowhere near what we said we would do in the Paris Accord. So we're still a long ways away from decreasing our carbon emissions to where we want them to be. But this is sort of a test, sort of pumping the brakes and showing you what would happen if you did start to emit less carbon dioxide and start to flatten out that carbon dioxide curve that's so well described by the Keeling curve from Mauna Loa.
So if we look at the reverse and you got maximum ice pack, how much more land is there?
Quite a bit. I mean, at the peak of the ice age, sea level was about 300 feet lower than it is today. So you can imagine the continental, what's called the continental shelf. At peak ice age, you could drive east from Washington, D.C. about 60 or 70 miles onto what is now seafloor. And as a result, there's lots of interesting archaeological sites that are buried under the are covered by 200 or 300 feet of seawater now that had been coastal encampments back then. In fact, in my office here in the museum, I have part of a mastodon skull that was dredged up off the coast of Virginia by fishermen. It has a spear point in it. So someone speared a mastodon 18,000 years ago in what is now 200 feet of seawater off the coast of Virginia. So this story goes both ways. It's an amazing, amazing story.
In that worst case scenario with sea level rise, how much landmass do you think we also lose due to just heat, the down by the equator or other places where it becomes uninhabitable because it just gets too hot?
Yeah, that's sort of a separate thing. One of the challenges is if you warm the world enough, there will be areas in the equatorial regions where it would be not possible for humans to work outside in the middle of the day. You basically wouldn't be able to shed enough bodily heat. So there's areas that would be kind of lethal to be outside. Now you could continue to live in those areas if you continued to have air conditioning and living inside, but it'd be more like being on a different planet because you wouldn't be able to have humans doing agriculture, for instance. You could drive around in your air-conditioned car to your air-conditioned building, but if you got trapped outside and you were trying to do anything or walk somewhere, it might be lethal. So we do see that as one of the big threats is that much of the equatorial regions would enter a zone where it becomes very difficult to survive if you're doing things outside.
Can you speak just for a minute about general regions? You've mentioned like the Pacific Northwest and Alaska and some other regions that you've been to, but just if you're out on your morning walk and you're because we've got people joining us from all over, what are some telltale signs that there are fossils around that people might look for?
Yeah, so fossils are in sedimentary rocks, and most places that have forests, you don't see rocks too often because forests cover the rocks. If you're living in a place where there's not a whole lot of rainfall today, you'll get deserts. And in deserts, I mean, paleontologists love deserts because there's no vegetation covering the rocks. Sort of when the landscape is naked because there's not much vegetation, you can literally see layered rocks. Anytime you see layered rocks, they're going to be fossils. So all the classic outcrops like Grand Canyon or the Badlands of South Dakota, those kinds of landscapes, you can see the fossils pretty easily. In places like Washington, D.C. or Washington State or Alaska, there's lots of rainfall, there's lots of trees, you usually find fossils in places like road cuts or construction sites or beaches where the bedrock is being exposed either by natural erosion or by humans digging holes. And in places like California and Los Angeles, most construction sites have interesting fossils in them, and there's salvage paleontology going on. And even in Los Angeles, there are things like fossil whales that show up when people dig highway excavations. So fossils are pretty common. Almost every state in the union's got fossils, and lots of them. Probably the most fossil poor state is Maine because the rocks there are so tortured the fossils have been cooked and baked out of existence. But almost anywhere else, you have a pretty good chance of finding a fossil. And the best place to go see them is your local museum.
And actually, are there other ways to sort of get involved with your local museum in a period of quarantine?
Well, I think most natural history museums now are doing a lot of digital online activity. And if you go to any of our websites, you'll find lots of webcasts with curators. You'll find virtual tours of the museums. A lot of the museums during non-quarantine time have volunteer programs that engage people in citizen science or community science, where people can actually get their hands dirty and work with the scientists. In our case, collecting fossils or excavating things or collecting scientific data. So museums are actually, it's sort of interesting now with this quarantine, museums seem closed. But the fact is they're just a buzzing hives of researchers working away out of their bedrooms, their homes, working on the digital data they've collected from the collections and their field excavations. So all the scientists that work here at the Natural History Museum, all 400 or so scientists are busily doing science, even though the museum is closed. And even our collections people are doing work on cleaning up scientific data from around the collections digitally from their homes as well. We're all eager to get back to work, I can assure you that, though.
So as you consider and talk about climate change, I'm guessing you've probably encountered folks who just don't share that whole worldview. It's just outside of the construct of what they believe. Do you have strategies for engaging and talking to someone who just basically says, I'm not on board with climate change?
Well, yeah, my basic approach is to find some common ground, like find out how they get their information, what they believe in. Do they get information from scientific journals, or do they read websites, or do they get it from their minister? Who's telling them what they are believing in? And I like those conversations because I think that it's really important to realize that facts alone don't convince things. They don't convince people about things. And if someone doesn't believe in climate change, it might not be because they're ignorant. They might actually know quite a bit about geology and climate, but they may have a different view of how that data is interpreted. It might be that they're more concerned about the impacts of climate mitigation, so they're worried about what we would do to deflect climate change from happening than actually climate change itself. So my goal is always to find common ground and have a calm conversation and see if there's some space where we can actually find something to agree on, and then dig into that area and see if we can actually make things make sense to people. And I find that paleontology is really useful because those petrified trees in Arctic Canada are hard to argue with. This is not a model. It's not a mathematical thing. I have a fossil alligator from Alaska. It must have been warmer. I mean, there's real evidence the climate has changed in the past. And if it's changed in the past by natural processes, there's no reason it can't change in the future by human processes. And using fossils is a pretty nice in because most people don't deny the existence of dinosaurs, fossil palm fronds, and those sorts of things. And I think the Polar Extremes Nova show that I did goes to great lengths to explain how we know what we know and make the story of Earth's climate past accessible and understandable. And then map onto that issues about, well, how am I involved? And there's a sequence in Polar Extremes where we demonstrate the amount of carbon that's in a gallon of gas, because everybody's pumped a gallon of gas into their car, but they don't think about what happens to that gallon of gas. And it turns out that 1 gallon of gas weighs 6.5 pounds, but 5 of those pounds are elemental carbon. And when you burn 1 gallon of gas, you get 18 pounds of carbon dioxide gas, but it's invisible, so you don't see it. But if that carbon came out of your tailpipe as solid chunks, you get a 5-pound bag of charcoal briquettes for every gallon of gas that you burn. If your car was dropping briquettes on the ground, you would know that you were leaving carbon as a byproduct of driving your car. So things like that that are simple and related to your everyday activities are also very helpful.
So I just want to say apologies to be jumping around in topics a little bit. We're getting a lot of response to you, which is fantastic. So please, everybody, keep the questions coming. One question is, so you spoke a little bit a moment ago about how to identify that you're in fossil country and there are fossils around you. But can you talk a little bit about how to identify what a fossil is? We've had questions both about plants and about animals in general, like how you got a fossil, now how do you figure out what it is?
Yeah, so fossils, any evidence of ancient life, and usually fossils are pretty broken up. I mean, the process of being, to make a fossil, you have to be alive and then die, and then get buried deeply, and the stuff you get buried in turns to rock, and then it gets uplifted and eroded, and then the fossil is found. So it's a pretty long process to get there, and fossils can be, hundreds of millions of years old. So a lot of times when you're with a paleontologist walking along, they'll bend down and pick up a little thing that looks to you like a little piece of gravel. But in fact, they'll say, well, this is the left elbow bone of a crocodile. And you're like, how do you know that? And the fact is that the paleontologist probably has spent a lot of his or her life looking at crocodile skeletons, and he can recognize the left femur of a fossil crocodile. So there's a lot of knowledge in knowing how to recognize the parts and pieces of things. So imagine if I took your skeleton and smashed it up and then took a chip of one of the bones. The first question is, well, what part of the body is it? And then from what kind of animal did it come from? Oh, it's a primate, it's a human. Wow, it's a human rib bone. What's going on there? So there's that kind of detective work that goes on in identifying things. And sometimes you find beautiful, perfect fossils like that palm frond where it's dead clear that it's a fossil palm frond. Other times you find pieces or parts like, I have no idea what this thing is. So it's a knowledge of the living biological world mapped onto the crushed and fragmented fossil world that lets you figure it out.
So we have a number of people who are asking about sort of the day and night cycle as you get near the poles, and wondering how plants adapted to not having sunlight for long periods of time.
That's one of the most mysterious things about polar forests is that even though it was warmer, there was still a polar light regime, which means you had several months of darkness in the winter and several months of light in the summer. And you think about plants today that live through winters, plants do have a strategy for winter. It's called deciduousness. They lose their leaves in the winter when the ground is frozen, so the water can't move up the tree and support the leaves. You also have deciduousness in tropical dry forests. When it's so dry in a season, there's no point in having leaves because there's not enough water for the leaves. In both those conditions, you're not getting enough water in the dry or cold season, and you're not getting water in the cold season because the water is frozen, that the tree can't afford to have leaves on it. So one theory is that those tropical or those forests in the polar regions were deciduous forests. They dropped their leaves during the dark period and they grow them back. There's other ways. There are kinds of trees called evergreens, like various kinds of broadleaf trees and conifers that keep their leaves all year long. And a spruce tree in the boreal forest will keep its needles on all winter long. It just slows down its metabolism. And it's a little bit easier to answer the story of how the animals lived in those polar dark regions because plenty of animals today are nocturnal. So if you can survive a night and operate in the middle of the night, there's no reason you can't survive a winter night operate in the dark for 3 months instead of one night. So I think the animal question is easier to answer than the plant question, but the plant one remains a persistent challenge for science to understand just exactly how do those forests work.
So if you had the magic wand and you could make Earth healthy for humans or optimal for humans, what would that look like?
It would look like the world looked like about 2,000 years ago, probably. I mean, I think one of the things that we've done as humans is we've been pretty aggressively co-opting the best agricultural land, which used to be the best forest land. You think that the best kind of land is rich soils and ample rainfall makes for great agricultural regions. And you think about things like the cedars of Lebanon, there's not too many of those left because they've been cut down to make way for fields. And really good agricultural areas used to be really beautiful forests in many places. So I think if you wanted a landscape that was really healthy, you want to dial the clock back to where there's a little bit less human intervention in the landscape. Now that raises the question of where are you going to get the food? But we've been farming in a fairly inefficient way for many, many centuries. And more efficient farming might allow us to make more food with less land and thus leave more of these fertile, low-lying ecosystems for a more even balance between human and people on the landscape. Because ultimately we want to live in a world that's good for healthy, happy human communities, but also one where there's sustainable biodiversity that is well spread across the globe.
So how has, let's just say maybe over the course of your career, like how has technology changed the way you go about your work and how it stayed the same?
In many ways it stayed the same. I mean, in 1983, when I went to the Arctic, 84, we were flying around in helicopters, getting out with hammers and shovels and pickaxes. And but what we didn't have were GPS devices. So we didn't really know where we were. And at that point in time, interestingly enough, the magnetic North Pole was south of Ellesmere Island. So our compasses actually pointed south. So our compasses weren't very useful and there were no good maps. So actually locating ourselves in Ellesmere in 1984 was quite difficult. And what we used were air photographs. We'd take an air photograph and pin a spot on the air photograph. Now, when we went back to film polar extremes, we had GPS devices and we could say, well, plus or minus 1 yard, here's exactly where I am. So the geolocating devices are very good that way. And there's also other kinds of remote sensing devices that allow us to see into the ground a little bit better or to image the rock layers at depth a little bit better. And there's certainly a lot of technology that allows us to look at fossils much more precisely, like CT scans or micro CT scans that allow us to scan into rocks and look at the rocks. And of course, the use of radiometric dating techniques now allow us to precisely produce the age of a fossil. Back in 1984, I would tell you the age of a fossil plus or minus maybe as much as 2 or 3%. Now I can tell you the age of a fossil plus or minus 1/20th of a percent. So like if I'm estimating your age using an analogy would be, I could probably guess your birth date to plus or minus about a week using modern techniques applied to fossils. So we've been able to get much greater precision and much greater acuity and measure things. We can look at the isotope in the material and understand what animals were eating 50 million years ago. And we can understand growth rates of plants. So there's lots of cool new technology mapped onto that good old sturdy pickaxe and shovel technology.
And so, watching the way ecosystems change over time, does that give you key insights to plants and animals, and maybe even like land formations, like islands that would be at greater risk right now?
Oh, yeah, absolutely. I mean, I think it's the realm of ecology and geology together. It gets you to look at, why are certain things living where they're living now? And, you think about that original question I asked, which is why are those fossils in Republic, Washington? They're not living there now. Well, they used to live there then. So fossils basically give you the story of our planet. If you map them on the surface of the landscapes and you know where the continent's moving, you map the fossils, you can actually show how ecosystems have evolved and moved around. And today is just like is just when the musical chairs stopped. Like, here's where we are today, but you can go back, play that record all the way back for 500 million years and watch the evolution of modern terrestrial and marine ecosystems. And you can see what happened when ecosystems were dried up or got too cold or too warm. And we know quite clearly how to use that information to predict what's going to happen as we warm the climate. And one of the things we're going to see, and we're already seeing it, is trees are going to start moving north. There were forests 1,000 miles north of the tree line 50 million years ago. And now as we warm the planet, the trees are moving into the tundra. They're moving back to reform that ancient landscape. So in a way, we've seen this show before for different causes, but we know in ways, in a general sense, what's going to happen as we warm the climate.
So you're looking at that, and also the human factor. What are areas of optimism? What are some things that you think are good?
Well, I mean, I'm a very optimistic person, and I'm very bullish on the whole future of the planet. And I think that what's remarkable to me is how much we have learned as scientists during the time that I've been a scientist. And it's just not that long. The last 30 years, science has just had an explosion in new knowledge, new techniques, new insights, new models. And we are very close to understanding quite well, we put all science together, how the planet works and how life works. Those are really profound insights that didn't exist 30 years ago. And we have the challenge of a growing human population. We're 7.8 billion people now. We need to have food and medicine and good ways of getting along with each other. We want to preserve the planet, and I think we have the tools to do it. And it's almost at a point where the scientists are ready to hand off toolkits to policymakers and politicians and say, here's a way to make the Earth work well and still allow people to live their lives in a happy, productive, and lucrative way, but also not burn out the planet over the next 80 years. So I think that's a challenge for our humanity, is to imagine the world of 2100 as you want to see it, and then build a plan to get to it. And not worry about the potential apocalypses, but really focus on the desired outcome on planet Earth for the 22nd century. And it's pretty important because a kid born today is only be 80 years old in the year 2100. So this is something that's relevant to everybody who's alive today, how we treat the planet and how we use human ingenuity and technology and science to build the planet that we want for the next century.
So I only have time for one more question. And I think sort of creating an amalgam of a bunch for folks who have questions about how nature might have impacted climate over time versus how humans are impacting nature over time. What are some ways or tools that you look to actually, connect volcanic activity to a change in climate? Are there concrete examples that you can point to say, nature was doing X, Y, or Z at X time, and we can see how that impacted climate a little bit more specifically?
Yeah, now there's a huge body of science, and I'd start you with the Polar Extremes Nova Show has a big resource set, what they call the Nova Polar Labs thing. If you just Google Nova Polar Labs, a number of different assets you can get there. And there's a number of short videos that talk about those specifics. How do we know that volcanoes created carbon dioxide? How do we measure that sort of thing? And those are portals into the science. And a lot of this is evolving science right now. And there are questions we still don't know the answer to, but we know the general shape of those questions. And this is where science is now. Is we are very close to understanding how the world works as a system of systems. And that's, it's now a race for the next century as we apply that evolving knowledge to the similarly evolving challenges. But this is where science and technology and communication of science are so very important, because we know so much now, and we have a lot of information that's well grounded in science. And this is what the National Academy of Science does so well in its reports, is to deliver very insightful things. I actually contributed to a National Academy report in 2011, which talked about how is the planet's history of climate relevant to the climate of the next 100 years. We're very much at that point now where we can take the knowledge we've gained over the planet's history and flip it forward to our benefit for the next century.
So, Kirk, you have the most succinct answers, and I just want to thank you for getting to so many questions. We had 127 questions out, so we got to as many as we could. My apologies if you asked a question in the audience and we didn't get to you, but they were great, and it's really clearly people really responded to the talk. So thank you so much for your time today. We really appreciate it. Is there anything else you want to add before Anne jumps on?
All I'd say is, go to museums, and support the National Academy of Sciences, and watch NOVA Polar Extremes. It's streaming right now easily, so you can watch it. It's a 2-hour special that pretty much gives a more fleshed out version of what I talked about here, with some really amazing locations. And it's a great thing to watch, Polar Extremes. And then once the museum's open, come back and see Deep Time, the National Hall of Fossils, which has the whole story of life on Earth laid out over 31,000 square feet. We opened it in June. It's all it wants right now is visitors. So let's get through this pandemic and get back to work on planet Earth.
Yeah, I think we're all looking forward to getting to go back to the Smithsonian on the other side of this, and hopefully we can have time to put you on a live stage too on the other side of this whole thing. Thank you so much.
Looking forward to it. Thanks so much, man.
Yeah, I'm not sure, Anne, are you there? We are.
I am here. Yes, I have not gone away. Are you kidding? I was listening to all of that talk, and I want to say thank you, Kirk, because it was totally worth the wait. We really appreciate it. And Rick is right. You are very succinct with your answers, because we never could have gotten through that many questions. In fact, I don't think we've gotten through nearly that many questions in our other events. So you win the prize. And I had on my notes to say exactly that, to go to the museums. If it's not the National Museum of Natural History, find the museum in your local area to go do that. But if you can come to Washington, I think that for me, the Museum of Natural History has a very special place in my heart. When I was a young mother and didn't have a whole lot of money to do sort of special things for my son, the thing that he most looked forward to, and every weekend he would ask, and of course, and I think this is true of many people, when you say the Smithsonian oftentimes means like one place. They don't think of it as the big institution. And he would say to me, can we go to the Smithsonian? By which he meant, can we please go to the Natural History Museum? And it was something that I always did. And it's one of his fondest memories from his childhood, is spending all of his time there. So everyone should go when they can.
Absolutely. Thanks so much, Anne. Thanks, Rick.
Thank you. Thank you. And thank everyone for being here. We very much appreciate the time that you've taken out of your day to join us for some science and to be part of our event. We really were so grateful to Kirk for joining us. And I think that certainly the number of people that signed in today and the questions we got tell us that you were also glad that he was here. We do have coming up next week another event. It's called Alone Together, Coping with the Stress of Social Isolation. It's COVID related, but really the Academy has just come out with a report recently on the impacts of social isolation to largely elderly populations, but more broadly on how it impacts our physical health. And so I think at a time that we're all sort of in an enforced isolation period, this becomes very real and relevant. So we have 3 experts who will be joining us, all of whom are psychologists. Jay Van Bavel from NYU will be with us. Diana Tamir from Princeton will be with us. And Julianne Holt-Lundstad from Brigham Young, who was on our committee, will be with us. And after that, on May 20th, we are going to try a virtual version of our very popular speed dating event. So put that
Science speed dating.
science speed dating. Yes, this is not an act. I mean, yeah,
No
we should make
dating.
that clear. No actual dating will be involved, but you'll be matching up with science. Yeah, in fact, we've sometimes invited scientists to participate in that, and we've gotten the response, "I'd love to do that, but I'm sorry, I'm married." And then we have to point out the National Academy of Sciences is not actually engineering dates. That's not what we're doing. So join us then, and in the meantime, be well, and we will see you next time.
Yeah, thanks for staying part of our community. It's such an honor and pleasure doing these events for you guys.
Yep, thank you.